Hey everyone. So today is our last lesson in trigonometric functions, which is on the tangent function. Now, the tangent function is actually probably a little easier than the stuff we've done in the last couple of days. There's not a whole lot we have to keep in our minds when it comes to tan. We need to have a basic understanding of what the graph looks like. We need to understand what the period of tan is. And just a few important points around the tangent function. But we're not going to throw in like an A value and a B value and a C value and a D value on a tangent function all at once, just like we would do on a sine or cosine graph. We're not going to do that. So if you want to grab your book, and we'll get started here on graphs of the tangent function. So what we're going to do says here, okay, when an angle is drawn in standard position, the ratio for tan of theta equals y over x. Now, that was something that we talked about when we kind of introduced the unit circle. We said that when we drew that triangle, let me draw you one actually. If I was in a unit circle situation here, and we had that triangle in standard position, we called that x, we called that y, and we called that r. And then we said, okay, so the sine of that angle is y over r, the cosine of that angle is x over r, and then the tan of that angle is y over x. Now, based on the other stuff we've done with the unit circle, we've also discussed that every coordinate point out here can be written as, remember, Calvary stampede, cosine goes first, so we have cos of theta, comma, sine of theta. And with our unit circle, we talked about the fact that if tan is y over x, then that really becomes the sine of theta over the cos of theta. So that's why we've also written it. We said tan of theta is y over x, but tan of theta can also be written as sine of x or sine of theta over cos of theta. Now, the tan of theta equals sine of theta over cos of theta, that is on your unit circle. So you do have that to reference. So what we're going to try and do is we're going to build, using our knowledge of the unit circle, we're going to try and figure out what the graph of tan looks like. It's very, very different from the graph of sine and cosine, which you'll see in a minute. So if you take a look at the table that I've given you, we have a few values here for x. I would like you to figure out what the y values are for the function tan of x, so tan of negative pi over 4, tan of 0, tan of pi over 4, and so on. Pause me and fill that in. Okay, so all of that filled in should look like this. We ended up with tan of negative pi over 4. Remember, if you were using your unit circle there, negative pi over 4 would be this guy right here. So negative pi over 4 is actually the same as saying 7 pi over 4 if you wanted to think of it as a principal angle instead. Tan of 0, 0, tan of pi over 4 is 1. Now, the interesting thing here was tan of pi over 2 and tan of 3 pi over 2. They didn't exist because you ended up, if you think about that from a unit circle perspective, pi over 2, think about what angle, where are we at pi over 2? Pi over 2 is right here. The coordinate point for that is 0, 1. So when I go y divided by x, I end up with 1 divided by 0. I can't divide by 0, and that's why I get, if you had just typed that in your calculator, you would have gotten some sort of an error message, but that's why I'm getting the error message. It can't exist because it's undefined, because we end up with a division of 0 there. Now, think back to anytime we have a 0, pardon me, anytime we have a 0 on the bottom of a fraction, what does that do? It creates one of two things. Either it's going to create a vertical asymptote, or it's going to create a point of discontinuity. Think back to your rationals. If it creates a point of discontinuity, I'd have to have the same factor on the top and on the bottom. I've got a 1 on the top and a 0 on the bottom. That's not the same factor over the same factor. So this is definitely going to create a vertical asymptote at pi and at 2 pi. Okay. Sorry, I've read my table wrong. At pi over 2 and at 3 pi over 2. Then at pi and 2 pi, so we're here and we're here. We could also look at 0 there as well. But at those points, this guy here is 1, 0, and this guy here is negative 1, 0. So I end up with 0 divided by 1, or 0 divided by negative 1. 0 divided by anything is still just 0, so those values are 0. So take a second and see if you can plot this on the grid that you've been provided with and see how we do. Maybe start with those does not exist. Draw those in as vertical asymptotes. Remember, if they're vertical asymptotes, you want them to be dotted lines. And then get a few points there and see what happens. So your final picture should look like this. Okay, so you've got your vertical asymptotes at pi over 2 and at 3 pi over 2. They were on your table. You also would have noticed one at negative pi over 2 right here. Remember that negative pi over 2 and 3 pi over 2 are coterminal angles, so they're actually the same angle. And then we could plot in the zeros pretty easy. Okay, so I had 0 and pi and 2 pi. I also have one at negative pi here. And then we noticed that we were at a quarter pi, we were at 1, and at negative a quarter pi, we were at negative 1. And that gives it this kind of curve right in here. But then, according to the asymptotes, the graph will always travel towards those asymptotes and never actually touch it. So then that gives us this overarching from negative infinity up to positive infinity. And that just repeats itself. So where the tan graph is very similar to sine and cosine is it's still a periodic function. There's something happening that repeats itself every certain interval. Now, for sine and for sine of x and cos of x, for those functions, that period, that standard period before we did any transformations was 2 pi. What I want you to notice with tan is it's actually a little different. The period for tan was the distance from negative pi over 2 to pi over 2. That's really telling us where that cycle is. And that's actually a distance of pi. So the standard period for tan is pi, or if you're talking in degrees, 180 degrees. Okay, so we're going to fill this stuff in together. The domain, well, like most things in life, when we talk about domain, the easiest way to do that is to say, okay, hey, listen, x can be everything, except it can't be this and this and this and this. So we're going to start with a statement that says, okay, x can be everything. But then we have to say what x can't be. And x can't be the asymptotes. Now, this one's a little tricky, and I want you to go back, think through a few lessons ago when we were reviewing angles in standard position. One of the things we talked about was writing in a general solution or a general form. So that was writing all those infinite amounts generally. And what we did is we wrote the first positive one and then the period of repetition after that. Now, x can't be any asymptote that we see here. So what's the first positive one? The first positive one is pi over 2. What's the period that it was going to take until I see another not positive or not available one? That'd be 3 pi over 2. So from pi over 2 to 3 pi over 2, that's where you all yelled pi at me. We're going to say x can't be pi over 2 plus the period. So we say x can't be pi over 2 plus pi n, where n is a member of the integers. Okay, so x is a member of the reals, but it can't be pi over 2 plus pi n, where n is a member of the integers. Okay, for the range, in sine and cosine, we actually had a specific minimum, a specific minimum and a specific maximum. We don't actually have that for tan because it's going to shoot down to negative infinity and shoot up to positive infinity. So we actually have y as a member of the reals for the range. And then the period we've already talked about. The period is pi for tan, or 180 degrees if you are talking in degrees. Okay, so when is tan of x undefined, and explain why. Now, in my introduction, I kind of started on that because I got excited about it. It's at pi over 2, and then every pi multiple after that. So it's at pi over 2, 3 pi over 2, this would be 5 pi over 2, 7 pi over 2, and so on. Okay, essentially any fraction over 2 ends up being one of these quadrantal angles here. And on both of those, we have a 1 or a -1. That's not really the point. It's dividing by 0. That's what makes it undefined. Okay, so in my explanation here, I've said the function tan of x is undefined when cos of x equals 0. This is because tan of x equals sine of x over cos of x. When cos of x equals 0, there will be a division of 0 in the fraction, causing tan of x to be undefined. This creates the vertical asymptotes in our tangent function. Okay? All right. Now, how far apart are the asymptotes? They actually define our period for us. So it's one period, which is pi radians, or 180 degrees if you're talking in degrees. Determine the general equation of the asymptotes. See if you can write that down yourself. And my hint is you already did it. You have already written that somewhere else in the last couple of questions. So go back for a second, see if you can find it. And what I want you to notice is it was actually the NPVs of your domain. So this time, instead of saying x can't equal that, we're saying x does equal that because we've been asked to do the equation of the asymptotes. Okay, so use the graph to determine y equals tan of x. Use the graph of y equals tan of x to determine each value. So tan of 2 pi, we're going right to 2 pi. We see that it's 0 there. I actually learned the other day how to use a highlighter here, so I could circle that right there for you. There's the tan of 2 pi. The tan of 3 pi over 2, well, that's right here. That's undefined, so we're going to say it doesn't exist. Tan of pi over 4, we already talked about. That was right in your table. Oh, sorry, that was the wrong one. Tan of pi over 4 is right here. And that would be a 1. And then tan of negative pi over 4 would be right here. And that would be at negative 1. Okay, so we'll put all those answers in. And we're good to go. Okay, determine the value of negative 3 pi, tan of negative 3 pi, and tan of negative 100 pi. Well, don't get stressed out about the negative 100 pi. What I want you to notice is this. At 0, the tan of 0 was 0. At pi, the tan of pi is 0. 2 pi, the tan of 2 pi is 0. 3 pi puts you back here. Tan of 3 pi is 0. 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi. Okay, so 100 pi, the tan of 100 pi, or negative 100 pi in this case, is going to be 0. Any full multiple of pi is going to put you somewhere here. And any multiple of pi over 2, so pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, is going to put you on the y-axis quadrantal angles, and so that would be undefined. So any whole number pi, the tan of that will be 0. Any fraction over 2, the tan of that will be undefined. So I'm just going to clear those drawings from the previous slide. And I've got 0 and 0. So write the general equation for all solutions in each case. So tan of theta equals 0. Where does tan of theta equal 0? Well, that's what we just talked about. It's going to equal here, and here, and here, and here, and here, and here. So it'll be 0 plus every multiple of pi after that. So when we do those general solutions, we say the first positive plus the period of repetition. In this case, the first positive is 0, so we don't actually need to say 0 plus something. We're just going to do the something. So we'll call that pi n, where n is a member of the integers. Tan of theta equals 1. Well, if you go back to your unit circle and you're thinking about the fact that tan is sine theta over cos theta, you're looking for a spot on your unit circle where the sine of theta and the cos of theta are the same thing. And that happens at pi over 4. And then it also happens at 7 pi over 4 down here, because they would both be negative 1 over root 2 there, or negative root 2 over 2 if you rationalized it. So I know that I'm going to get 1 at pi over 4, and I know that I'm going to get 1 at, do you remember what that guy was? This would be 4 pi over 4, so that's 5 pi over 4. So my first positive is pi over 4, and then the multiple that I have to go to get to there is actually pi. Pi over 4 plus pi gets me to 5 pi over 4, and then if I add pi again, that would get me back to a coterminal angle to pi over 4. It'd actually be 9 pi over 4. Okay, so we say pi over 4 plus pi n, where n is a number of the integers. Okay. All right, what is the period of y equals 3 tan of 4x? Now, when we talked about sine and cosine, we said that there's a relationship between the b value and the period. For sine and cosine, that was always the period is 2 pi over b. Now, the reason it was 2 pi over b was because 2 pi was the standard period for sine and cosine. Remember that for tan, that's not the standard period anymore. The standard period is pi. So for tan, the relationship is very similar. It just changes to the period's going to be pi over b. So if we look at this equation, the period, the b value is 4. And so we're going to have a period of pi over 4. Now, if you want to think about that from, say, a horizontal stretch, if we had started with the base function of y equals tan of x, y equals tan of 4x, I'm ignoring the 3 right now because that's a vertical and it's not going to affect our period. But changing y equals tan of x to y equals tan of 4x is a horizontal stretch of a quarter. If I do a horizontal stretch of a quarter, I take the initial period and I multiply that by my horizontal stretch factor. Well, pi times 1 over 4 is pi over 4. So either way, no matter how I look at it, I get a period of pi over 4. So similar question here. If the graph of y equals tan of bx has a period of 7 pi over 3, determine the value of b. So we're using the same equation, we're using the same relationship, just in the other way. So now we're saying b will equal the period divided by, the old period divided by the new period. So the old, or the standard period, was pi, and now my new period is 7 pi over 3. Now I wrote that left to right. I didn't write it as a vertical fraction, just so I didn't have a fraction in a fraction. Also, it makes it easier to do the math here, because when we're going to divide fractions, we just multiply by the reciprocal. So b becomes pi times 3 over 7 pi. My pi's will divide each other out, and I'm just left with a b value of 3 over 7. Finally, we're going to see if we can take all this knowledge and think about what a cotangent graph might look like. Now, a cotangent graph is the reciprocal of the tan graph. So some of you, if you remember 20-1 really well, you could think about all your rules for drawing a reciprocal graph. Go to tan, think about everywhere where you saw 0, the reciprocal of 0 is going to become an asymptote, and you could do all that sort of stuff, and you could get the right graph. I don't want you to do that here, though. I just want you to think more from a trig perspective. Remember that cotangent is cos of theta over sine of theta. So think about that, because then you're going to think about where those NPVs are. The NPVs for tan ended up being when I had a 0 on the bottom, which was when cos of theta equals 0. Now, similar thing here, but now it's not cosine on the bottom, it's sine on the bottom. So where does sine of theta equal 0? Sine of theta equals 0 at 0, pi, 2 pi, 3 pi. Okay, so those are where my asymptotes are going to be this time. So try a couple points. I want you to pause me for a sec. I want you to come up with the drawing on yourself, and then we'll compare. Okay, so you got your asymptotes in. You found where your zeros would be. Your zeros actually ended up being at the pi over 2 and the 3 pi over 2 and all those multiples. And then, pardon me, the other thing I'm hoping you found out was that cotangent actually is going to go in the opposite direction. So we end up going from the positive infinity, curving down to negative infinity. So you ended up with a graph that looks something like this. And that's it. That's all you need to know for tan. You need to think about the fact that if we throw in a b value, that's going to change your period, but you're going to really see that change right away, because you'll see those asymptotes are farther apart or shorter apart from each other. Okay? All right, so your job is to get through pages 216 to 220. And I do have a little note here. There is a student center from your workbook. If you want more practice, you can just click on this link here. In the PDF that I have on D2L of this PowerPoint, that link should be active. If it's not, just send me an email and I can send you the link. Okay, so that's it for tan, and that's it for trigonometric functions. Next, we're going to get into trigonometric equations and identities, which I am like super excited about. So we'll talk soon. Take care, guys.